What is a data frame? A data frame is a two-dimensional, labeled, column-oriented data structure in pandas that is built on top of NumPy arrays, making it both flexible and efficient for handling structured data. It organizes data in a tabular format with rows and columns where each column can represent a different variable or feature. One of the key characteristics of a data frame is that it has two axes, the row axis known as index and the column axis which contains the column labels. Unlike NumPy arrays, data frames are heterogeneous, meaning each column can store a different data type such as integers, floats, strings or even dates. This makes data frames highly suitable for real-world datasets which often contain mixed types of data. Overall, data frames provide a powerful and intuitive way to store, manipulate, and analyze tabular data in data science applications. Index objects. Index objects in pandas are used to label and identify both rows and columns in a data frame, and they play a crucial role in data alignment and selection. These labels are immutable, meaning once they are created, they cannot be changed directly, which ensures consistency and prevents accidental modification of data structure. Because of this immutability, pandas can perform operations like joins, merges, and arithmetic alignment very efficiently and safely. Indexes can be of different types such as integers, strings, or date time values depending on the nature of the data. In more advanced scenarios, pandas support multi-index which allows hierarchical indexing where multiple levels of indexing are used such as organizing data by region and quanta. This is especially useful for representing complex datasets with multiple dimensions. It is also important to note that columns themselves are stored as an index object, which means both rows and columns follow the same underlying indexing mechanism. Common operations. There are several common operations in pandas that help in understanding and manipulating data frames effectively. The attributes df.index and df.columns provide access to rows and column labels, while df.datatypes show the data type of each column, which is useful for identifying inconsistencies or preparing data for analysis. The function df.reset_index is used to convert the existing index into a column and replace it with a default integer index, whereas df.set_index allowing setting a specific column as the new index for better organization. The method df.rename_axis helps in renaming the index axis for clarity and better readability. Additionally, df.to_numpy converts the data frame into a numpy array, which is useful when raw numerical computations are required. These operations are fundamental for data preprocessing, cleaning, and transformation tasks in any data analysis workflow. The code example demonstrates how data frames and index objects work in practice. First, import pandas as PD imports the pandas library. Then, a data frame is created using a dictionary with columns A and B, and custom row labels R1, R2, and R3 are assigned using the index parameter. The statements print of df.index and print of df.columns display the index and column labels, showing how pandas internally represent them as index objects. Next, a multi-index is created using pd.multi-index from product, which generates all possible combinations of two lists such as regions and quarters, forming a hierarchical index. This multi-index is then used to create another data frame demonstrating how complex multi-level data can be structured efficiently. Finally, the function df underscore m dot reset of index converts the hierarchical index into regular columns, making the data easier to view and analyze. This example highlights how Pandas supports both simple and advanced data structure, which clearly enables flexible manipulation. It also shows that using Pandas, the data manipulation can be performed in a very powerful manner so that the efficient coding can be reproduced. Selector recap. Selecting entries in a data frame is a fundamental operation in Pandas, and choosing the correct method depends on whether we are working with labels, positions, or individual values. Pandas provides multiple indexes that allow flexible and precise data access, and these can also be combined with Boolean conditions for filtering. The goal is to retrieve specific rows, columns, or cells efficiently without introducing errors. Understanding when to use label-based selection, position-based selection, or scalar access methods is important for writing clean and reliable code. Additionally, combining these indices with Boolean masks enable powerful filtering operations, allowing us to extract only the data that satisfies certain conditions, which is a common requirement in data analysis tasks. The iLock indexer is used for label-based selection, meaning it works with row and column names rather than positions. It supports slicing, selecting multiple labels, and even Boolean filtering, making it very flexible. For example, we can select specific rows and columns using their labels or apply conditions directly within it. On the other hand, iLock is used for position-based selection where indexing is done using integer positions starting from 0. This is particularly useful when the exact position of data is known or when working with ordered data sets. The .at and .iat methods are optimized for accessing a single value quickly. The .at method uses labels while .iat uses integer positions. These are especially useful in loops or situations where repeated access to individual elements is required, as they provide faster performance compared to general indexing methods. The code example demonstrates how these selection techniques are applied in practice. First, a data frame is created using sample with label rows and columns. The line x is equal to df.log of r2, a retrieves a value using label-based indexing, while y is equal to df.log of 0, 1 accesses a value using position-based indexing. The expression sub is equal to df.log of r1, R3, A selects a subset of rows and columns using labels. Boolean filtering is shown using high is equal to df.log of df of A greater than or equal to 20, A, B, which selects rows where column A satisfies a condition. For faster scalar access, df.at of r1, b and df.iat of 2, 0 are used to retrieve individual values efficiently. Finally, the query function is demonstrated with a condition-based selection written in a readable format. These examples collectively show how Pandas provides multiple powerful and flexible ways to access and filter data effectively. Why this matters in EDA? Reindexing and dropping entries are essential operations in exploratory data analysis because they help in organizing data into a consistent and meaningful structure. During analysis, datasets often contain missing labels, extra entries, or inconsistent ordering, which can affect results and interpretation. Reindexing allows us to standardize labels to ensure that expected rows and columns are present even if some values are missing. At the same time, dropping unnecessary rows or columns helps remove noise and irrelevant information, making the dataset cleaner and easier to analyze. These operations are especially useful when preparing data for reporting, aligning multiple datasets, or maintaining consistency across time series data. Overall, they help to improve the data quality without losing traceability of changes. Reindexing is the process of conforming a data frame to a new set of labels for rows or columns. When we use functions like df.reindex of new index or df.reindex of columns equal to, pandas rearranges the data according to specific labels. If a label in the new index does not exist in the original data frame, Pandas introduces it and fills the corresponding values with NaN by default, although this can be controlled by using the fill value parameter. Reindexing works for both rows and columns, making it very flexible for reshaping data. This is particularly useful in scenarios like time series analysis where we may want to ensure that all time points are present, or in reporting templates where a fixed schema is required. It helps align data across different sources and ensures consistency in structure. Dropping is used to remove unwanted rows or columns from a data frame based on their labels. Using functions like df.drop of index equal to or df.drop of columns equal to, we can explicitly specify which entries to remove, improving clarity and control. This is useful when cleaning data by eliminating irrelevant or redundant information. The parameter errors equal to ignore can be used to prevent errors if the specified labels are not found, making the code more robust in automated pipelines. After dropping rows, the index may become non-sequential. So df.reset underscore index of drop equal to true is often used to reassign a clear continuous index. Dropping operations are a key part of data preprocessing, helping to refine datasets before analysis or modeling. The code example illustrates how reindexing and dropping works in practice. First, a data frame named base is created with a column A and a custom row labels. The line re is equal to base.reindex of R1, R3, R4, fill value equal to 0, rearranges the rows and introduces a new label R4, filling its value with 0 since it did not exist before. Next, re underscore calls equal to base.reindex of columns equal to a comma b adds a new column b which is filled with nan because it is not present in the original data frame. The statement renum equal to base.reset underscore index of drop equal to true resets the row index to a default integer sequence. For dropping operations, drop underscore r equal to base.drop of index equal to r2 removes a specific row, while drop underscore c equal to base.assign of b equal to 1, 2, 3 dot drop of columns equal to b first creates a new column and then removes it. These examples demonstrate how Pandas provides flexible tools to reshape and clean data efficiently. Labels drive results. In pandas, data alignment plays a crucial role in how arithmetic operations are performed, and the key idea is that labels drive the results rather than positions. When performing operations like addition or subtraction between series or data frames, pandas first aligns the data based on index labels for rows and column names for columns. This means that values are matched using their labels, not their order. If there are mismatched labels between two datasets, Pandas automatically takes the union of those labels and fills missing values with NaN. This behavior ensures correctness and prevents accidental misalignment of data, but it also means that users must be aware of label differences. To handle missing values introduced during alignment, functions often allow specifying a fill value. Understanding this concept is essential because it directly affects the outcome of arithmetic operations and is a defining feature of pandas compared to traditional array-based computations. Pandas provide several useful functions to manage alignment and perform arithmetic operations effectively. The method s1.add of s2, fill value equal to 0 allows element-wise addition between two series while replacing missing values with a specified default such as 0 to avoid any end results. The align function is another powerful tool that explicitly aligns two datasets before performing operations. For example, a.align of b, join equal to outer, fill value equal to 0 ensures both data frames share the same index and column structure, filling missing entries with the chosen value. Additionally, the combine first method is useful for filling missing values in one dataset using corresponding values from another dataset. These tools provide flexibility in handling mismatched data and allows users to control how alignment and missing values are treated during computations. The code examples demonstrate how alignment and arithmetic operations are implemented in practice. First, two series are created with different index labels when s1.add of s2, fill value equal to 0 is executed. Pandas aligns them by labels and performs addition, filling missing entries with 0. As a result, the output contains all labels from both series with correctly computed values. Next, two data frames A and B are created with partially overlapping row labels. Using a.align of b, join equal to outer, fill value equal to 0 produces two aligned data frames with the same index, allowing safe arithmetic operations like addition using a2.add of b2. Another example shows alignment using an inner join on columns where only common column labels are retained. These examples illustrate how Pandas automatically manages alignment and provides functions to control and customize this behavior, making it highly effective for data analysis tasks involving multiple data sets. Fast EDA Toolkit. Sorting, ranking, and summary statistics form a core toolkit for quick exploratory data analysis, helping us understand the structure, distribution, and patterns within a dataset. Sorting allows us to arrange data in ascending or descending order, making it easier to identify trends, top values, or anomalies. Ranking assigns positions to values based on their magnitude, which is especially useful for comparisons, leaderboards, or identifying relative performance. Summary statistics, on the other hand, provide a compact numerical description of the data, including measures such as mean, median, standard deviation, and range. Together, these operations help analysts quickly detect outliers, understand variability, and gain insights into the dataset without needing complex visualizations. The function sort underscore values is used to order data based on one or more columns, and it supports multi-key sorting where different columns can have different sorting directions. The rank function assigns ranks to values, and it provides multiple methods to handle ties such as average, minimum, maximum, first occurrence, or dense ranking. Dense ranking assigns consecutive ranks without gaps, while average ranking assigns the mean ranks to tied values. The describe function generates summary statistics for numerical and categorical data, providing insights such as count, mean, standard deviation, and percentiles. Additional functions like AGG allows custom aggregation of specific metrics, and CORR helps in understanding relationships between variables by computing correlation values. These functions together provide a comprehensive way to analyze and summarize data effectively. Why multi-index? A multi-index in pandas is used to represent higher dimensional data within a two-dimensional table by introducing multiple levels of indexing for rows or columns. Instead of having a single label per row, a multi-index allows combining multiple labels such as region and quarter to form a hierarchical structure. This is especially useful when working with complex data sets that naturally have multiple dimensions such as time periods, geographical regions, or product categories. By organizing data in this way, we can perform more precise selection, filtering, and reshaping operations without needing separate tables. It essentially allows us to store and analyze multidimensional data efficiently within the familiar data frame structure, making it a powerful tool for advanced data analysis. Creating multi-index. A multi-index can be created in multiple ways depending on the structure of the data. One common approach is to convert existing columns into index levels using df.set_index of region, quarter, which organizes the data frame hierarchically based on those columns. Another approach is to generate a multi-index from combinations of values using pd.multi-index from product, which creates all possible pairs from given list such as all regions and quarters. This is useful when defining a structured grid of data. To ensure consistent and predictable slicing operations, it is also important to sort the multi-index using sort_index, as many hierarchical operations depend on sorted levels. Proper creation and organization of a multi-index makes it easier to navigate and manipulate complex data sets. There are several important operations that can be performed on multi-index data frames. The cross-section operation using df.access allows selecting data based on a specific level or a full key, such as retrieving all values for a particular region or a specific combination like region and quarter. Slicing across levels can be done using pd.indexSlice along with df.lock, enabling flexible selection across multiple index levels. Reordering levels using functions like swap level and then sorting them with sort index helps in reorganizing the structure for better readability or analysis. Reshaping operations such as unstack and stack convert data between different formats, for example, turning a level of the index into column or vice versa. These operations provide powerful ways to navigate and restructure hierarchical data effectively. From sources to data frame. Data acquisition is the first and most critical step in any data analysis workflow, as it involves bringing external data into a structured format like a pandas data frame. This process is not just about collecting data, but also about ensuring its reliability and quality before analysis begins. Data can come from various sources such as web apps, open data sets, or web scraping, and each source requires specific handling technique. Once the data is fetched, it must be validated to check for correctness, completeness, and consistency. Additionally, documenting the provenance of the data, such as where it came from, when it was collected, and under what conditions, is essential for reproducibility and trust. By following a structured approach from source to data frame, analysts can ensure that the data is ready for meaningful analysis. Web APIs, open data, scrapping. These are three common ways to acquire external data. Web APIs provide structured data, often in JSON format, which can be easily converted into a data frame using functions like JSON normalize. APIs may require handling pagination and retrieve to fetch all available data reliably. Open data sources typically provide files such as CSV or Parquet, which can be directly loaded into pandas using functions like read_CSV or read_Parquet. These are commonly used for publicly available datasets from governments or organizations. Web scraping, on the other hand, involves extracting data from web pages, often using tools like Read HTML for tables or libraries such as Beautiful Scoop for more complex extraction. Each method has its own advantage and challenges, and choosing the right one depends on the structure and availability of the data. When acquiring data in real world applications, it is important to follow best practices to ensure robustness, reliability, and compliance. Respecting rate limits and rules specified in robots.txt is essential to avoid overloading servers or violating usage policies. Including a proper user agent helps identify your application when making requests. Implementing timeouts and retry mechanisms ensures that temporary network issues do not disrupt the process. Handling pagination carefully is necessary to retrieve complete datasets when data is spread across multiple pages. Data validation is another key step where checks are performed on required columns, data types, uniqueness, and missing values before proceeding with analysis. Additionally, caching new data and recording metadata such as source URL, timestamp, version, or query parameters helps maintain reproducibility and traceability. These practices make pipelines more stable and maintainable. The code examples demonstrate how data acquisition is implemented in practice. First, a web API is accessed using the request library where a GET request is sent to the specified URL with parameters like timeouts and headers. The response is checked for errors using raise for status, and the JSON data is extracted and converted into a data frame using JSON normalize. Pagination is handled using a loop that repeatedly fetches data from multiple pages until no further data is available. Next, open data sources are accessed directly using functions like read underscore CSV and read parquet, which loads structure files into data frames efficiently. Finally, web scraping is demonstrated by extracting tables from a web page using read HTML, which returns a list of tables that can be further processed. These examples show how Pandas integrates with different data sources and tools to create a seamless data acquisition workflow. Web APIs, open data, and web scraping are three important methods used for collecting data in modern applications. A web API allows different software systems to communicate and exchange data in a structured and real time manner, which is widely used in applications like weather services, payment systems, and mobile apps. Open data refers to freely available public datasets provided by government and organizations which support research, data analysis, transparency, and innovation. Web scraping, on the other hand, is used to automatically extract data from websites when APIs or open datasets are not available, making it useful for market research, price comparison, and trend analysis. Together, these techniques play a crucial role in data collection, enabling effective decision making and supporting various data science and analytics applications. Summary: in this unit, we explored the fundamental concepts of NumPy and Pandas, which are essential tools for data analysis in Python. We began with NumPy, understanding how it provides efficient multi-dimensional arrays and enables fast computation through vectorization and broadcasting. We then learned how to create arrays, inspect their attributes, and perform operations like slicing, reshaping, and sorting, along with understanding memory concepts such as views and copies. Moving to pandas, we studied series and data frames as powerful structures for handling labeled and tabular data. We explored how indexing helps in selecting and filtering data using log, ilog, and Boolean conditions, and how to transform data using sorting, grouping, and aggregation techniques. We also covered important concepts like reindexing, handling missing values, and data alignment during arithmetic operations. Finally, we looked at advanced topics such as multi index for hierarchical data and methods to acquire data from APIs, files, and web sources. Overall, these tools together provide a strong foundation for efficient, scalable, and real world data analysis. Thank you.